All right, so let's look at number 1 first. We've got, find the measure of the angle in degrees using correct algebraic sign plus or minus. If I take 2/5 rotations counterclockwise. Counterclockwise is positive direction. So we can just call that 2/5 rotation. I'll abbreviate it here. And then 2/5 rotation needs to be converted to degrees. So I'll say, how many degrees are in one rotation? Well, there's 360 degrees for one rotation. I put rotations on the bottom here to cancel rotations on the top here. And I've got just 2/5 of 360 degrees, which I think comes out to be 72 degrees, is it not? Let's see. No, it's 144. Yeah, 144. Thank you. Okay, so 144 degrees. That's what you do on that one.
Oh, okay.
And then 7/12 clockwise. Is minus 7/12 rotation. And again, you multiply by 360 degrees for one rotation. See, the 12th of that is 50, is it not? Let's see. It's 15, right? From 7. So it comes out minus 210, you're saying? Yeah, okay. Ever see that guy use the human calculator? He takes these 7 or 8 digit numbers and multiplies them right in front of you in a couple seconds. I can't believe I can't do it, as you can see. Okay, so there's that one. What else would you like to see? Okay, let's look at 5. Says the terminal side of an angle in standard position passes through the indicated point. Calculate the values of the 6 trig function. So the terminal ray of theta, let's say, goes through the point minus 724. Find the trig functions. And we said, if you know a point on the terminal ray, you know all 6 trig functions, even if you don't know the angle. Find the trig function values. In some books, they actually initially introduced trig functions like this. You say, you have any point like minus 7 and 24, whatever it is. The sign is actually defined to be y over r, and the cosine is x over r. Instead of using unit circle, though, to find it for general points like that. But we can do this and say that, what is this angle? Well, we know how to do it on the unit circle, right? So I can take the point on the same terminal ray that's only 1 unit out, 1 unit. How far out is this one? Oops, not that one. This point that has coordinates minus 7, 24. Remember? How far out is it?
You do the Pythagorean theorem to find it.
There you go. Yeah, you drop the perpendicular, use the Pythagorean theorem. It's square root of negative 7 squared plus 24 squared. If you work that out, this one I memorized. It's 25. I'm not a human calculator. That's a Pythagorean triple, 7, 24, 25. So that's 25 units out. The one in the same direction, 1 unit out ought to be where? I have what coordinates? Got to be 1/25th of these coordinates, right? Since they're 1/25th of the way out, it ought to be minus 7 25th, 24 25th. All right. Wait a minute, that's a point on the unit circle. So what's the x coordinate? Oh, I'm a failure. Cosine, there you go. Yeah. Thank you. Cosine theta must be minus 7 25ths, and sine theta must be 24 25ths. And once you know sine and cosine, you know all the rest by the reciprocal and quotient identities, right? For instance, what's tangent theta now.
Sit over adjacent.
You could do that actually in this big triangle if you prefer. Instead of doing this, you can just say, well, sine is this over this and cosine is this over this. That's probably easier. I was gonna say tangent can take sine over cosine, and so it's minus 7/24. But it's probably easier to use this big triangle here, right? And say, this one over, oops, must be the other one. It's this one over this one. Minus 24/7. Sine over cosine. But yeah, so make this big triangle is an easier way. You can say cosine is adjacent over hypotenuse, sine is opposite over hypotenuse, tangent. But you have to keep the sign as the trick. So you have to keep the negative. This one. Or if you use the unit circle, you can it tells the negatives. All right, so the cotangent is then the reciprocal of the tangent. It's minus 7/24. The secant is the reciprocal of cosine. You just turn it upside down. Secant is minus 25/7. And the cosecant is the sine upside down. Secant, sorry, is 25/24. Hope you can see that. That's what you can do is just take a unit circle. It's got 1/25 the radius, so you just divide those coordinates by 25. And then you got cosine and sine, and you get the others really easily. Turn these upside down and get these two. Take the quotient to get this one, and reciprocal to get that one. Yeah, that's a good question, because those are tricky problems, but those are good because they're applied problems. That's what you'll probably see when you go to work. I'll expect you to do, right? They won't give you the unit circle. They'll give you some point out in Kentucky or something. What else would you like to see today?
Number 3 always tricks me out, the clock.
Okay, number 3. So hopefully that's visible now. Yeah, you notice I put a couple of additional applications on here that we didn't do everything up before. One of them is the clock. Oh, I think we mentioned this briefly. Clock hand begins, the second hand begins on the 2, and 2 minutes and 12 seconds pass. What angle has the second hand swept out? So I think it's nice to draw a picture on this one. And here's 12, 1, 2. It doesn't actually matter where it starts. So I like to start on the 12. So I'm going to say start on the 12. It sweeps out the same angle regardless of where you started, right? And so if I let 2 minutes and 12 seconds pass, in 2 minutes, 12 seconds, you get, well, 2 minutes is 2 rotations. 12 seconds is 12/60ths of a rotation, right? There's 60 minutes in a rotation, or 60 seconds in a rotation. So it's 2 rotations and 12/60ths of a rotation. And they're clockwise since it's a clock. So this is 2 and 12/60ths is 2 minus 2 plus 12/60ths rotation. Oh, good. Thank you. Okay. Appreciate it. Okay. Apparently our room is working. I think it's working in here, so I'll go ahead and continue. I'd rather see this again, but there was some funny script messages coming up here saying it couldn't read some of the script, so it's just a little worried. I'll have to check on it. All right, so this is how many rotations. Now we remember how to convert rotations to, what was it we wanted in here? Said what angle. Since I didn't say, I suppose you can leave it in rotations almost, but if I convert it to degrees, well, this is 120/60ths, right? Just multiply top and bottom by 60. Plus 12 gives you, you sum the numerators, minus 132/60ths. Right? And now that's rotations. Converted to degrees, I'm again multiplied by 1, 60 degrees for every one rotation, and then cancel the units of rotations. And let's see, 360 over 60 is 6, so I can just rewrite this as minus 132 times 6 degrees. So I got 600, 780, 792 negative degrees. And you think, does that seem right? Yeah, it's a little bigger than 2 rotations. That's probably right. There's the clock problem.
And you would just prefer to have it on the negative 792, or you like to drop that down to like below 360?
No, this is the whole rotation. I want the 792, yeah. Yeah, that's a good point. If I say 72 degrees, that's just telling you the direction. It's not telling you what's the whole rotation.
Right.
Okay. One thing I absolutely want to ask you to do is solve a right triangle. If I give you 2 sides, or if I give you an angle on the side, I want you to be able to solve it. Can you do those all right? That's number 4. If alpha equals 22 degrees, A equals 4.30 inches, solve the triangle and round to 1 decimal place. Given that it's a right triangle. So I sketch it here. The sketch has B over here and beta over here. A over here and alpha over here, and then C the hypotenuse as usual. So I'm given these 2 and I know a right angle. I have 3 more things to find, right? There's 3 angles and 3 sides, and this is a total of 6 things. This is 3 of them. So I relate these 2 things, alpha and A, that I know, to one that I don't know. Maybe I want to find the hypotenuse. So this is the opposite side to alpha, and the hypotenuse, I could say I want to use the sine. The sine of alpha, 22 degrees, would be A over C is 4.30 over C. You could also use cosecant. It relates these 3, but then cosecant isn't on your calculator face, so you're gonna have to change it to sine sooner or later anyway. Now I just these 2 are equal, their reciprocals are equal, so I can say therefore 1 over sine 22 degrees C over 4.30. And I did that so I can solve for C. This becomes equivalently 4.30 over the sine of 22 degrees to C. So I can run that in my calculator. Making sure it's in degrees mode, right? And I got 11.48 when I rounded to 2 places. Actually, since it said round to 1 decimal place, I'll write it as 11.5. All right, so there's C, and now I can find the other values. For instance, I know I can relate B to the 2 I'm given and say tangent of alpha is opposite over adjacent to alpha, right? Here's the side opposite alpha because it doesn't help form alpha. This is the leg that helps form alpha, so we call it the adjacent side. Tangent alpha 22 degrees ought to be A, that I know, 4.30 over B, and I can find B that way. Actually, you know what? Easier than that, what we've been doing is saying, once you find one of these, just use the other 2 properties and say sum of angles theorem theta is 90 minus 22 degrees is 68 degrees, and then Pythagorean theorem is usually easier using trig again, but use trig again if you want. We'll say that the last side, B, is in the square root of the hypotenuse squared minus the other leg squared. So it's 11.5 squared, or you can carry more digits if you want. And I'll count it right either way. Minus 4.30 squared. Comes out to be something. Square root. Let's do it the same way we've been doing. I'll use the Pythagorean theorem. Let's see, I get 10.7. And then the units originally here, I think were inches. So this is gonna be in inches. And this is gonna be in inches. I'll be able to do that for sure, because I'm gonna ask at least one problem, either in 4A or 4B.
Why didn't we have sine 22 degrees equals 4.30 over c?
Right.
Why didn't we just multiply both sides by 4.30 to get?
Or divide both sides by 4.3? You can do that if you want to.
No, like multiply, like
If I multiply both sides by 4.3, I won't get rid of the 4.3 on the right. I'm just trying to clear, use algebra however you want. What I decided to do was take reciprocals and then multiply both sides by, or you mean from here? I multiply both sides by 4.3, hopefully. Yeah. 4.3 times the left side is 4.3 over sine 22, and 4.3 times the right is c.
I think what you're trying to do is, it's the way I do it. So you actually multiply c, so it'll be c sine 22, then you divide sine by 22, which leaves you with 430. Divide that by sine 22. You can't multiply the bottom denominator or the top denominator with the other side. You always have to divide the bottom denominator.
This is what he's saying. Maybe that's what you're saying too, is you can start from here and instead of taking reciprocals, there's lots of algebraic ways to do it. Multiply both sides by c and get c sine 22 equals 4.30 from this step instead of taking reciprocals. And then you can divide by sine 22 to see it's 4.30 for sine 22. Yeah. That's a great way to do it. I do it that way, it's down the board sometimes. I can switch back and forth. Either way is great. Okay, if I give you one trig function, can you find all six in a quadrant? Can you find all six from that? That's another kind of classic problem that's on here. Like a number 14 is kind of tough. I told you, I gave you one. I give you cotangent in the quadrant, can you find 5 trig functions? Or how about number 18 is kind of a tricky applied problem. This one says an observer stands here measuring from eye level at 5 feet. Along a lamppost out here. So this is a lamppost. And finds that the observer knows they're standing 20 feet from the lamppost. So that's a right angle right there. The angle of elevation is 37 degrees. The angle of elevation is up from horizontal. And tall is the lamppost. This is all I gave you, okay? So I'll label H for the whole height here. I'm trying to find how tall the lamppost is. These applied problems are kind of sneaky because you almost have to draw the picture. If I don't give you a picture, draw it in order to figure out what's going on, because I may need both these triangles depending. All right. Well, here's one thing that picture tells you immediately, assuming horizontal ground, which you're supposed to assume unless I say otherwise. And if this is 5 feet, this is also 5 here. This is the right angle here. Yeah. And so on this triangle, I have two sides that I know. And on this triangle, I have an angle on the side. I can solve both those triangles, right? That's what we memorized from the last other problem. So I can solve this one. You can call this one x if you like, and say to relate x to 20 as tangent, right? Opposite and adjacent. I'll say tangent of 37 degrees is x over 20. And I can solve for x out of that. And then let's see. Oh, that's all I need because I have the 5 here. I could solve this triangle if I needed to, though. All right, and then x plus 5 will give me h from the picture. So we'll just multiply this through by 20 and say x, and switch sides. X equals 20 tangent 37 degrees. All right, so I multiply by 20 and switching sides. I get 15.07. And now the height from the picture is just x plus 5 is 20.07. So what's that, feet tall, I assume? And I don't know if it said around a particular spot, maybe nearest foot or something.
Yeah.
Okay, so then you'd say it's just 20 feet. Okay, that's not too bad. Huh? The picture just makes an amazing difference sometimes. You just you write down all the things you're given, and then you say, oh, I see now, this is 5 also, or this angle is such and such. And once you know, this one, if I just find it plus 5, gives me the height.
Also do 14 like you were talking about.
Okay. Now, this is one of the hardest problems on here, I think, but you guys did pretty well on the quiz, so maybe you'll get it. 14, if I'm given one trig function, I can find all of them, but the hard case is given tangent or cotangent. Given that the cotangent of an angle is equal to 2 with angle in quadrant 3, find the other 5 trig functions values. We'll abbreviate function FCN here. And on the test, I said, or the quiz, I said, one thing you can do is immediately use the Pythagorean identity. From this one, you can get cosecant immediately, right? Because cotangent squared plus 1 is cosecant squared. You can figure that out. But I also said another nice way to do it is this. You can do it, I don't care which way. So we did this one since then. Cotangent theta is 2. I can write that as 2 over 1. And if I divide top and bottom by the root sum square of those numbers, right? The root sum square of 2 and 1 is square root of 5. I'll find out that this is 2 over square root of 5 over 1 over square root of 5. Right? I just divide the top and bottom by the same thing, so the same quotient. And then I'll say, wait a minute, in quadrant 3, are sine and cosine positive or negative? They're both negative, right? So I'm going to rewrite this as minus this one over minus this one to be in quadrant 3. And now this one will be the cotangent is cosine over sine. If I get the right sign plus or minus on each of these, then the top one's the cosine, the bottom one's the sine. Immediately out of there, I get cosine is minus 2 over square root of 5. Right, this is cosine over sine. And sine of this angle is minus 1 over square root of 5. And once I have those, I have all the others by the quotient reciprocal identities. Might be easy to find tangent by turning this one upside down. Tangent is 1 over the cotangent is a half. We do reciprocals for all the rest. In fact, secant is 1 over the cosine. This is turn that one upside down, minus 5 minus square root of 5 over 2. And secant, cosecant. This one upside down. minus square root of 5.
So if you were to go the route of, like, let's say instead, like, so my brain doesn't work that way. If I looked at it and I said, okay, cotangent is 2, and then I just immediately say, okay, well, let me just do the tangent, because.
Yeah, do that.
So then
It's all good later anyway.
so from the tangent, how can I go get the sine and the cosine?
Yeah, there's still multiple ways, and I hate to do too many ways, like I just make it confusing, but here's another way. You can say that you know this trig identity, remember the Pythagorean identity, 1 plus cotangent squared equals cosecant squared. This is the one everybody has the hardest time remembering because it's the least used, which makes cotangent sort of the hardest case. So I use that and I'll say, well, 1 plus 2 squared equals cosecant squared. 5 equals cosecant squared. So cosecant must be square root 5, plus or minus. Is it plus or minus? You have to go quadrant 3. So cosecant must be minus the square root of 5, where the minus is because it's in quadrant 3. Now, once I have cosecant, I've set because sine is the reciprocal of that. Probably you remember this one. The cosine can always be found as plus or minus the square root 1 minus sine squared. This is the easy Pythagorean identity, solve for cosine. And you choose minus because it's in quadrant 3. Well, let's see, what is this? It's minus the square root, 1 minus a fifth. Well, this is 5/5 minus 1/5 is 4/5. Square root of 4 is 2, so it's minus 2 over square root of 5. Now, once I've got sine and cosine, I'm home, right? So I can do secant by taking 1 over this one. Secant 3 minus square root of 5 over 2, just turning it upside down. And I got the others. We did tangent was 1 over the cotangent. For half. And then I've got all 5. And then so you use the Pythagorean identity as another way to do it. Get one of the other trig functions, and then you can get all of them. Cosecant is reciprocal be sine. Sine will give you cosine. This is key. Whenever you get sine and cosine, you know everything you did. Right?
I think another way easier of doing it is just drawing it out. You
Yeah,
just draw out the
that's how I-
angle.
Yeah, that's what I was gonna say. Some people did it by drawing it out on the test, and so there's another way if you like to do it that way. A lot of people like that. Looks like to do it that way, so this is a good way. I just like this way. It's easy for me. Yeah, if you draw it in quadrant 3, and you say the cotangent is 2, all you have to do is make a triangle over here. You can do it on the unit circle, or you can just do any triangle, and say the cotangent is the x over the y, so this has to be ratio 2 to 1. But if it's in the third quadrant here, then some people like to label these with negatives. I like to put triangle links on there. But coordinates here at least are -2, -1. And you can figure out all the sine and cosine, for instance, sine, and then this side has to be by the Pythagorean theorem, square root of 1 squared plus 2 squared is square root of 5. Then from the triangle, you say cosine is this 1 over square root of 5. 2 over -2 over square root of 5. Sine is this 1 over the hypotenuse is -1 over square root of 5. You have to label the sides with negatives as you do it this way. And et cetera, right? Tangent do the reciprocal, or you can say it's this 1 over this one. -1 over -2 is a half, and so forth. See, you can now do reciprocals always. I'll say et cetera. So that's a really good one. Some of you did it that way. Probably read the book. Right? Yeah.
I actually do have a question. If I remember correctly, quadrant 3 is the only place where tan is positive, right? Regardless if it's both negative. If I remember correctly.
Tangent and cotangent are both positive in quadrants 1 and 3.
Okay.
Yeah. Everything, here's a nice way to remember it. They're all positive in quadrant 1, right? Because you just get a triangle with all positive sides. And then in the other quadrant, you just have to figure, like if you're in quadrant two, I don't memorize which quadrant all that much. I just kind of visualize it and think, well, if I'm in quadrant two, then sine on the unit circle, then sine is this positive value, but cosine is the negative value. If I'm in quadrant three over here, they're both negative. Cosine is x and sine is y. And so I just think of sine and cosine on the unit circle as the y and the x coordinates. But for cotangent and tangent, it's a ratio of two sides, and here if one's positive and one's negative, you get a negative. So you get tangent, cotangent, negative here, and also over here, you get one positive and one negative, so you get a negative cotangent, tangent here, but over here where they're both negative, you get a positive tangent, cotangent.
I remember all students take calculus,
Yeah, okay,
and all for quadrant one, students is the sine, and quadrant two is
Yeah.
positive. Calculus is the cosine, is negative in three,
yeah,
and all the rest are positive, and then, yeah, so.
yeah, yeah, that's a good one, I've heard before too. If you like, I think those kind of things, that's great too. I like pictures. So, yeah. Depends on whether you're a geometer or an algebraist sometimes. Geometry, pictures, and algebraist, like.
I had a question on number 9.
Okay. Still working. Looks like it is, yeah, okay. Find a positive angle and a negative angle that's coterminal. Positive and negative angle. Coterminal with each of these. (540 degrees). What you do is you just keep subtracting 360 until you get the last positive angle. So if I subtract 360 once, what have I got? I've got 180 degrees. That's the one I want. I don't want to subtract it twice, or I'll get a negative, right? If I subtract 720 twice 360, I'll get a negative. So that's that one. And then on B, if I get a negative angle, like minus 225, I just keep adding 360, add 360, add 360 until the first time I get a positive angle, and that'll be it. So I add 360 once, that'll already make it positive. That gives me what, 135 degrees? So that's the coterminal angle.
Yeah, because see on the answer sheet, there's actually 2 points. You got positive 135, and then you got negative 585. And I'm wondering how you got that negative 585.
It's subtracting 360 from the thing, I guess, from negative 225.
Oh, yeah, you know, here I was trying to get an angle that, is between 0 and 360. But here on the handout, I just said find a positive and a negative angle, so you can find out whatever you, yeah, I'm sorry, so here's a positive one. Yeah, so the problem just said find a positive and a negative, so here I can subtract 360 to get a, all right.
I see.
I was finding a coterminal, so there's a positive angle. If I subtract 360 again, I can get a negative. So if I subtract 720, then I get a minus 180. Yeah, so I'm sorry, I just guessed the instructions, yeah. If I say find a coterminal angle between 0 and 360, then you do this. If I say find a positive and negative, then just add or subtract to get a positive, and add or subtract to get a negative, whatever mole of 360 you want. So you can add 100 times 360, it'll probably be positive, right? Subtract 100 times 360, it'll probably be negative. That works, so you can do that if you want. Yeah, so now I can subtract 360 from this. Any multiple of 360 can be added or subtracted, you get a coterminal angle. So let's say this is minus 585. So there's more than one solution on this one. Infinite number of solutions.
Let me see if you can look at number 15.
Okay. problem. Golfer. This is an unrealistic problem because real golf courses are not flat. What makes them fun is they have stand traps and everything. But we're with a golfer on flat ground, so because we said we'll assume that anyway, unless it says otherwise. This is the first hole or something where you're just getting going and make it easy on you. Golfer on flat ground, sees a flag whose tip is at an angle of 2 degrees. Elevation. Horizontal. Find the distance the golfer is from the flag if the flag is 5 foot tall. But in here sees a 5-foot flag. 5-foot long flag tip at 2 degrees elevation. Find the distance to the hole. See if you have your handy dandy sextant, you can measure how far it is in every hole. Then with 3 now. Find the distance to the hole. Then you know what iron to hit or whatever. Draw the picture in an applied problem, right? Here's the golfer standing here. Assuming the golfer measures from the ground, and this is 2 degrees. The height of the flag, here's a little 5 feet. And what you want to find is D. So write everything you know and what you want to find. And now you see it, right? Oh, I see. What relates these two numbers I know to the one I don't? Tangent does, right? Because it's opposite and adjacent. Tangent is 2 degrees. Is 5 over D. I can use cotangent and get D over 5, but then it's not on my calculator. So now I can multiply by D. Let's do it the other way, like suggested here. D tangent 2 degrees equals 5, and divide by tangent 2 degrees. D equals 5 over tangent degrees. Now what do we get? This is actually, you gotta have a careful instrument for this one because you measure 3 degrees instead of 2 degrees, it's gonna be pretty far off, right? But let's see, 5 divided by tangent 2. I get 143 feet since this was in feet.
That's fair. I just read the question. I guess I had trouble. The 2 elevation part was throwing me off.
Oh, yeah, okay. Yeah, one of the things out of this course also is to learn all this terrible terminology that people use. That we're gonna run into, like, so many degrees west of north and, you know, those kind of things that are coming up. Yeah.
Like, bro, I keep
Yeah,
thinking-
that'll do you in, won't it? Okay,
Let's see if you can also review 20.
okay. Let's take a look at that one. Yeah, and that's a good week. You only got one day of new material. You can do it this weekend, right?
Oh, it's great. I caught up. I'll tell you that.
So, use the unit circle to find exact values theta. Theta in 0 to 2 pi. Yeah, this is one I expect you to do too. This is very likely to be on the test. Such that A cotangent theta is minus the square root of 3. And in 0 to 2 pi. What does this notation mean? 0 to 2 pi?
Circle.
Pretty square brackets on both ends, isn't it? This is probably hard to read with all these lines. And the interval 0 to 2 pi. It's clear up here because the lines are separated, but back there it's probably a jumble, right? what this notation means is that whatever variable it is between these two values. So this is just, notation for theta between 0 and 2 pi. And the square bracket means include equals. But if you had this, 0 to 2 pi, the round bracket means don't include the endpoint. So this would be 0 strictly less than theta, less than or equal to 2 pi. So you can do things like this with square and round brackets. But that notation for angles is important in this question. All right, so we want theta between 0 and 2 pi because this notation was given. These you solve on the unit circle and you say cotangent theta yeah, this is the way I like to do it. I like to write it as minus square root 3 over 1. And then I'll take the roots on square of those numbers. Square root of minus square root of 3 squared plus 1 squared is square root of 4 is 2. So I can rewrite this by dividing top and bottom by the roots on square. Minus square root of 3 over 2, 1 over 2. And now if I get the correct sign, it'll be, one will be, the top will be cosine and the bottom will be sine. But here's what you do. Actually, okay. There's two choices here. So this is equal to this, or it can also be this. Go over these lines. It could be minus square root 3 over 2 over a half and get this negative ratio, or it could be square root 3 over 2 over negative a half, and that also gives the ratio. So there's two choices here. You can either have cotangent is x over y. On the unit circle, you can either have this x and this y, or you have this x and this y. So this one would be x negative minus square root 3 over 2 and a half, and you get this point. It'll be that angle. Or you can put x to be plus square root 3 over 2 and y to be minus a half. And you get this point. And they're always directly opposite. And so those are the 2 points in the unit circle that you gather give you this ratio for cotangent. Now what angles are those? You can drop the perpendicular and say, wait a minute, it's square root 3 over 2 on this side and 1/2 on this side because it goes up to a half, right? 1/2 square root 3 over 2. So it's a 30, 60, 90 triangle. This is, since I said, by the way, if it says 0 to 2 pi, that means I want the answer in radians. If it says 0 to 360, then I want the answer in degrees. So this one I want in radians. I need this 30-degree angle in radians. We memorized it as pi over 6. 30, 60, 90 triangle, 30 degrees is pi over 6. And then similarly by symmetry, this is pi over 6. So once you have one, then you have the other. But tangent and cotangent, it's always the opposite angles, but they have the same values for tangent and cotangent. What we do is we say now that this is 30 degrees, then and this angle that I'm interested in must be 180 minus 30 degrees. 150 degrees, right? And then this one here, I'm looking for angles between 0 and 360, I think it said, right? Is 360 back up 30. Oops, I should have written that in radians. 2 pi back up pi over 6 gives you 11 pi over 6. You do the quotients there. And this one would be 2 pi back up pi over 6 is 5 pi over 6. So this is 5 pi over 6 pi back up pi over 6. And this one here is 2 pi back up pi over 6. Whole rotation 2 pi back up 30 degrees is pi over 6 gives us 11 pi over 6. So there's two solutions out of that. 5 pi over 6 and 11 pi over 6, this angle and this angle. But that picture on the unit circle is immensely helpful. That's how I like to do it. Write this as a ratio, divide by the root sum square, one is cosine is the other sine, but there's, you can put the negative on either one. At 24, just because we didn't really do that one before. If we'll be on the test or not, but when you have a gear, of radius 15 centimeters. You know, when I was a kid, they were bringing in the metric system and it was gonna take over and we're all gonna be on uniform in the metric system and all those English units, feet, yards and miles was all gonna go away and boy, this never happened. We're still hanging on to it today. I can't believe it. But, I mean, they're both used quite a lot, but for some reason, the English units are still being used. What happened to that big movement? Anyway, a gear of radius 15 centimeters. So we're doing both in this class, as you can see. Turns a gear radius 8 centimeters. If the larger gear turns 120 degrees, how far does the smaller gear turn? This one is good for visualization. But since an applied problem, draw pictures, this would be immensely helpful. I'm just gonna draw the gears as circles. By the time I draw the teeth on the gears, they never looks right. So here's a 15 centimeter radius gear. Turning, here it's just a little over half the radius, 8 centimeters. And they've got little jagged teeth in here, so it turns without slipping. And that's key to this problem, right? Because, actually, let's put the 15 here just for simplicity. And say, suppose this turns 120 degrees, that's 90 and 30 more, so it's about here, right? Right angle, a third of a right angle. There's 120 degrees roughly. If it turns without slipping, then when it turns through this arc length from the gears meshing to here, the other one turns the other way. The same arc length, right? If their gears are meshing properly, then it's the same arc length. So that's the trick on here. And what you say then is that the arc length this one turns, S, is equal to 15. It's R theta, R1 theta 1. Is also equal to R2 theta 2 over here. Right? So the radius times the angle, since they both turn the same arc length, S, these two are equal. That's what the gear problem is. You say R1 R theta 1 equals R2 theta 2. So this is 15 times 120 degrees equals 8 times theta 2 that I want to find. Oh, wait a minute, maybe I boo-booed. This formula only works in radians, right? This formula only works in radians, but if you convert both sides from radians to degrees, you can leave this in degrees, right? Because you convert both sides to radians by multiplying by pi over 180, right? So now it's arc length on both sides, but then you can cancel the pi over 180, multiply by 180 over pi on both sides. So this formula, R1 theta 1 equals R2 theta 2, works either in degrees or radians because I can cancel the conversion factor out. So I'll just write it like this, even though this isn't S anymore. You multiply by pi over 180, or get S. We don't need that. So we'll just write this, radius times angle equals radius times angle and leave it in degrees, then I'll get an answer in degrees. So I just divide by 8, theta 2, what I want to find is 15 times 120 over 8. There's a very, very subtle error in here. What did I do wrong?
Question.
Hmm?
It's a good question.
That's a tricky one. I will accept this as the correct answer, actually. I won't mark it off, but I might mark something. The gears turn opposite directions. If this one turns a positive 120, then this one actually turns a negative angle. So you should really technically put this, but then you can't put the S in the middle. So actually this should be R1 theta 1 equals minus R2 theta 2. This is then minus that. I don't care if you don't do it. Then you want to simplify it also. So we'll say theta 2, the second one. Is, let's see, 60, 30, 15, 15 minus 225 degrees. Divided that by 8. 15. Yeah. It's pretty good. I got a special angle out of each. I got turn 120 degrees out of this one. Get 25 out of that one. Won't get that lucky.
About 22.
Okay, let's see that one. Find the distance that a point travels along a circle over time t, given that the angular speed. Oh, good. I wanted to do one an angular speed. Given that the angular speed omega is pi over 5 radians per second. The radius of the circle is 30 centimeters. Round to 3 significant digits. So find distance traveled along a circle by a point if the angular speed is omega is the usual letter, pi over 5. It's just angular speed, so it's radians per second. And circle radius is 30 centimeters. And the gear turns for 5 seconds, 20 seconds. So the circle turns 20 seconds. I think the hardest part almost is just setting this up. Again, since it's an applied problem, we'll draw a circle. And we'll set draw a picture. And we'll say, well, the point starts here just to be convenient. And it travels around and around and around. And the angular velocity it's turning at as it turns through here is pi over 5 radians per second. And it turns for 30 centimeters. What are we trying to do when we find out how far does it turn? We're finding the arc length going around and around a circle. So we say the arc length S, that's the distance traveled. Is the radius times the angle it turns through, right? Well, what's the angle it turns through? You remember that omega is equal to the angle divided by time if it's turning a constant velocity, constant speed. Theta divided by time. And so theta is equal to omega t. I told you these things are tricky, even though they're straightforward. So theta can be replaced by omega t. So the arc length that travels is r omega t. This is the radius, this is the angle it turns through. The angular velocity times the time gives you the angular distance traveled, the angle. And You just have to make sure it's in radians. Unfortunately, it's given that way. So R is 30 centimeters. Omega is pi over 5. Sorry, my phi looks a lot like my seconds here. This is a seconds, this is a pi. Pi over 5 radians per second times t is 20 seconds. Okay. And you should write your units because they can be tricky, right? If this one's in minutes and this one's in seconds, then you got to convert them to cancel. Evidently, they're both in seconds here, so I'll just cancel them. The centimeter stays, it doesn't cancel, but the radians can go away because it's units. And sure enough, I get centimeters, distance traveled. So that's my hint there. So I need 30 times pi times 20, the sum of the product of the numerators over, think of this as quotients. 1 times 5 times 1. So it's 30 times pi times 20 all over 5. And sometimes it's better not to multiply these out right away because 20 over 5 is 4. This is just 30 times 4 times pi. So it's 120 pi. Exactly. Answer may have asked you to round it to something with decimal places. I don't know, but it's 120 pi is the exact number then.
360.
Okay. So 3 significant digits then is now, let's try. Just to make sure you didn't cheat. 120, guess it, right? Times pi. Gives me 77. Would be 3 significant digits. What you do with significant digits is start with the first non-zero digit and count 1, 2, 3, and then you're done. So I'm comes to the nearest whole number. It's actually 376.991. I'd like to stop and so we'll round it to 377. The significant digits, you start with the first non-zero digit, 0 through 9, and 1 through 9 for a non-zero digit and count over. Decimal places, you count over the decimal point. That's 2 decimal places and you put. Some of these problems you've seen before, hopefully look like we can do them. I'm going to see if there's something stand out that I really need to do. Go ahead and ask questions if you want.
$33.
Okay. Oh, yes, here's one I can ask you. Hate to see you miss this one because it isn't hard, but if it's there's 33. Want to be able to do a trig function of any special angle exactly, whether it's in degrees or radians. So find exactly, use the unit circle for this normally, the cosecant of minus 11 pi over 4. How about that? Here's the first thing you do if you see cosecant or secant, write the reciprocal and find that on the unit circle. So I'm instead going to find 1 over the sine of minus 11 pi over 4. That's the trick to get started. Right? And now on the unit circle, I can find sine 11 pi over 4 because it's a special angle, right? Any multiple pi over 4 or pi over 6 is special. Well, this is minus 11 pi over 4, the multiple pi over 4. So I'll now go and look at, to get minus 11 pi over 4, I'm going to write it out as minus minus 8 pi over 4, because that's 2 rotations, right? Or excuse me, 1 rotation clockwise, and so this is, 1 rotation is 2 pi, or 8 pi over 4. Clockwise. And then that leaves me another minus 3 pi over 4, right? So the sum of the numerators, minus 8 minus 3 pi all over 4 is minus 11 pi over 4. Now, how do I do that? Well, I'll pull out another factor of pi, a straight angle. So I pull out the whole rotations, then I pull out the straight angles, minus 8 pi over 4 minus pi. Let's call this minus 2 pi. Minus 2 pi. 3/4 pi is pi. Another quarter. Pi over 2. Oh, it's not a straight angle. I need at least pi. This is 3/4 pi. If I pull out a right angle, pi over 2. 1/2 pi and 1/4 pi makes 3/4 pi. I just broke that into 1/2 and 1/4 instead of 3/4. And so I got 1 rotation, 1 right angle, 1/2 of a right angle. This one. And they're all clockwise. So you draw that angle. If I ask you to evaluate any trig function of a special angle, you draw using this strategy is a good way to do it. Take out the whole rotations, take out the straight angles, take out the right angles, look at the fraction of the right angle, and it should come out to be a special angle. I can't ask you to do it exactly. The calculator, if you bought a good calculator, can check all of these exactly and see if you got it right, by the way. So clockwise, a rotation, a right angle, and 1/2 of a right angle. That'll be in all minus 11 pi over 4 since I went clockwise. It's right there. Now I drop a perpendicular. This was pi over 4. It follows that this must be pi over 4 here. Pi over 4 and pi over 4 makes pi over 2 a right angle. So it's a 45, 45, 90 triangle. This is 1 over square root 2, and this is 1 over square root 2. Again, I'll draw positive leg lengths. But now, sine is the y coordinate. Minus 1 over square root 2. Well, the reciprocal of 1 over square root 2 is square root 2, and this just comes out to be then minus square root 2. Okay. That's what you can do to find a trig function of any special angle. Rewrite it in terms of sine and cosine. If it's cosecant, write it as 1 over sine. If it's tangent, you write it as sine over cosine. And then on the unit circle, find sine and cosine by looking at the point. It's a good way to do it. There are other ways that are similar. Here's number 30. Suppose I want to simplify that. Soon we're going to get harder problems with this. This is kind of gets you started. Hey, suppose I gave you secant theta times cotangent theta. How can I simplify that? Here's the big trick on these. Anybody got a good idea for what trick would work for this? Yeah. How do I simplify an expression of trig function? Here's a big hint. Try writing them all in terms of sine and cosine. All right, so if I write secant, it's 1 over cosine. And I write cotangent, that's cosine over sine. And now I notice the cosines cancel. This is just 1 over sine. And now I see 1 over sine as cosecant. So there it is. This is just a fancy expression for cosecant. Right? Similarly, on the next problem, 30b, if I have cosecant divided by secant, that slash means divide. What is that? Well, if I write cosecant as 1 over sine, and I write secant as 1 over cosine, let's write them all in terms of sine and cosine. Then I've got top times bottom over middle times middle becomes cosine over sine. Once it's in terms of sine and cosine, I recognize immediately, oh, that's cotangent. So this one is a fancy expression for cotangent. But you want to be able to do that. People always expect you to simplify these things. You don't want to write cosecant over secant when it's just cotangent, right? McDonald's, they say, oh, I see your hamburger is 3/4, 2 dimes, and 2 pennies. Okay. All right, well, I guess you guys are ready. It looks like it says it's time to go. If you want to answer a couple more questions, otherwise we'll go ahead and I'll see you tomorrow for the exam. On Monday, do you want to meet in the outdoor classroom or would you rather just?
Depends how hot it is.
What?
It just depends how hot it is. It's all.
Okay. Yeah, Monday is a little up in the air. It's supposed to be real hot in a couple days here, but it's supposed to be a little cooler on Monday at the moment. It kind of makes you sit out in the sun. Keep it the outdoor classroom one more time and see if we like it. No, do you not like it? Tell me if you like it. Okay, let's, all right. All right, so we'll try it on Monday, and if it gets too hot, there, bring it.
Can you actually remind me?
Monday at the outdoor classroom, yeah.
Can you actually remind me the similarity triangles again? The number 26, for example.
Okay, you can go if you want class is over, but I'll do 26 real quick for anybody who wants to stay. I almost did one of those. Do something. Here's 26. And I'll put these problems in this lecture online if you want to look back at any of these. 26 is this picture. These two are parallel, this one and this one. This is 8, 12, x, 9. Find x, right? Sure, these are similar triangles because these are parallel. This is the same angle in both triangles, right? And that, if the parallel lines, that makes these congruent, and then consequently these can go 180 degrees. So what you can do is say that x is to x plus, let's do it easier. X is to 12, this side is to this side, as, let's see. In fact, there's more than one way to do this. I think there's an easier one. Now, the easiest way to do this, I'm going to take a little shortcut just for time. Say x is to 9 as 12 is to 8. It's not actually one of your theorems for similar triangles, but let's do it this way. Yeah, let's just, all right. Let me write it the way this theorems are on the book. X is to 12, this one is to this one in the small triangle, as this one is to this one in the big triangle. X plus 9 is to 20, this one. So you can write like that and then solve it for x as an algebra problem is the idea. But you take once the ratio of two sides in a little triangle, the ratio of two sides in the big triangle. And you can solve that by cross multiplying. Get 20x equals 12x plus 9 times 9 times 12 is 108. And so now you can just solve that. Subtract over 8x equals 108. Right. X equals 108 over 8. Let's see. 13.5, I guess. There we go. I do it like that though.
Okay, thank you.
Yeah.
It's always that setting up is the issue with those.
No, that's the trouble. You're up, you can't win. Everybody have a good day.